Hi everyone, my name is Dishita Turakhia and I'm a PhD student at MIT with Professor Stefanie Mueller, and I'm very excited today to talk about Adapt2Learn, a toolkit for configuring the learning algorithm for adaptive physical tools for motor skill learning. Let me begin with recapping some of the prior work in the area of motor skill learning with adaptive physical tools. We presented this work at TEI recently, where we showed that adapting tools based on learners' performance can significantly improve results in motor skill learning. So for example, in the case of learning to throw basketball in the hoop, we built an adaptive basketball stand that adjusts its hoop diameter and adapts its hoop height as the learner improves in their skill. The goal is to use physical adaptation to adjust the task difficulty such that it is neither too hard nor too easy for the learner. Our studies showed that such auto-adaptive training led to higher learning gains when compared to conventional static and manually adaptive training methods. A key contribution for achieving this auto-adaptation was the learning algorithm that we developed. This algorithm sensed the learner's performance and adapted the tool to maintain the task difficulty at the optimal challenge point at all times. So while in our prior work, we showed that the physical tools that adapt using our learning algorithm can help in motor skill training, the next question that remained unexplored was how can we help support designers in the design and creation of such adaptive tools for various motor skill learning. We addressed this question in our current work, where we first conducted a formative study to understand the challenges designers faced in creating adaptive training tools. We then built Adapt2Learn Toolkit to support designers in addressing those challenges. And finally, we built several applications to evaluate the generalizability of Adapt2Learn. Let us start first with the formative study. We conducted this study for 8 weeks in a bi-weekly design studio format with 32 participants grouped in teams of 2. We asked the teams to design, prototype, and build an adaptive training tool for a motor skill of their choice. By letting the teams choose the motor skill themselves, we were able to explore the design space of adaptive training tools for various motor skills and identify the common challenges in building them. Participants started with brainstorming 10 ideas each and then selected one idea per team that they used for designing and prototyping their tool, and finally for user testing. During the 8 weeks of study, we observed their design process, prototype implementation, and the algorithm development. Finally, we conducted semi-structured interviews with 8 volunteering participants. And we were quite impressed with the variety of creative designs developed for a wide range of motor skills. The applications range from sports, for example, this adaptive skateboard that sensed the learner's balancing skills and adapted the board length, to music, for example, this adaptive piano that sensed the learner's note timings and actuated the keys to lift up and down. There were applications in other motor skills, such as learning sign language using this adaptive glove, and even walking in heels using this adaptive heels, where as the learner's balance improved, the heel height is increased. In the study, we observed that the participants faced several challenges in different stages of creating adaptive training tools. In the design stage, the participants found choosing the appropriate sensors and actuators challenging. Please refer to the paper for design guidelines we provide to help designers with this step. In the implementation stage, they face a common challenge of quick prototyping and building robust hardware. We don't address this challenge as there are several toolkits in HCI to help designers with this aspect. Finally, we observed that the step that several teams found most challenging was the step of creating the learning algorithm. Only 5 out of 16 teams deployed an algorithm of some form. Because this challenge is unique to the motor skill learning, our work focuses on supporting designers with this step of creating learning algorithm for their designs. In particular, the teams faced 2 specific challenges. First was configuring the learning algorithm itself. This involved mapping the sensor values to the actuator values such that the performance sensed caused the adaptation of tool's task difficulty optimally. We observed that there was no standard way of developing the learning algorithm, and one of the teams said that the biggest challenge for them was optimizing the learning algorithm, which was quite brute force at the moment. The second challenge was assessing if the algorithm used was working optimally as desired. As another team pointed out, the problem was not knowing if they had come up with an optimal solution. To address these 2 challenges, we built Adapt2Learn Toolkit. Adapt2Learn Toolkit has two components. First, to help designers with configuring the learning algorithm, we built a user interface that designers can use to configure their sensors, actuators, and respective threshold values, and our UI auto-generates the learning algorithm for their tool. And secondly, to help designers with evaluating the generated learning algorithm, we built a visualization tool that shows them how the tool is adapting according to the learner's performance in real time. I will now quickly demonstrate how the user interface works with a walkthrough of the configuration process. And I will use the example of adaptive basketball from earlier. The first step is for designers to register sensors and sensor states in the UI. So for example, we register a piezo sensor to detect a board hit, and register the piezo values for board miss as a failure state and values for board hit as success state. Designers then register additional sensors, that is the switch sensor to detect a basket hit, and then register the switch values for basket miss as a failure and basket hit as a success state. The second step for designers is to register actuators and actuated states in the UI. So for example, we register a servo motor to tighten and widen the hoop and register the servo rotation values for hoop widening as failure state and hoop tightening as success state. Similarly, designers register additional actuators, that is the stepper motor to raise or lower the stand. And then register the stepper motor rotation values for stand lower as failure state and stand raise as a success state. Finally, designers define evaluation units and generate the code. This code is a microcontroller script with our learning algorithm that is auto-generated and customized for the physical tool. It can now be deployed to the microcontroller and used to adapt the tool for motor skill training. To evaluate if the auto-generated code with the learning algorithm is adapting optimally, we also built a visualization tool that plots in real time the chart of learners' performance, their improvement in scores, and the moments when the tool adapts to a harder or an easier setting. This visualization helps designers in assessing the timing of adaptation with respect to the learner's skill levels and check if the tool is adapting optimally. To test if Adapt2Learn generalizes for various designs and sensor actuator combinations, we built several examples. We built and configured an adaptive armband with single sensor actuator combination. This armband supports learners in keeping their elbow straight during a golf swing. It has a flex sensor to detect if the learner's elbow is straight or bent, and a pneumatic pump that deflates and inflates the armband to restrict bending of the elbow. We built and configured an adaptive Wobble Board with a combination of 2 synchronized sensors and 1 actuator. The Wobble Board has an inflatable cushion that supports learners in learning to balance the board. We mounted 2 ultrasonic sensors on opposite sides of the board to detect if it is stable or wobbling, and a pneumatic pump to deflate or inflate the support cushion that restricts wobbling. We also built and configured an adaptive bike with a combination of 2 synchronized sensors and 2 synchronized actuators. The bike has adaptive training wheels that help the learners with learning to balance the bike. We mounted Hall effect sensor on each of the training wheels to detect how often the training wheel is being used, and mounted stepper motors on those training wheels to lower or raise the wheels based on learners' performance. Please refer to the paper for more details on implementation and additional examples from the user study. In future, we would like to expand the types of sensors and actuators that are supported in our UI, which is currently 8 types of sensors and 4 types of actuators. We would also like to add the functionality of being able to reconfigure the learning algorithm in real time during the training. And finally, we plan to evaluate the usability of Adapt2Learn Toolkit with designers during different phases of their design. In summary, in this work, we highlighted the key challenge in design of adapting tools is deploying the learning algorithm. We showed how Adapt2Learn can support designers in configuring the learning algorithm for their respective designs, and how Adapt2Learn generalizes for various designs and sensor actuator combinations. With this work, we can support designers to further explore the design space of adaptive training tools. And with this, I look forward to the discussion, and I'm happy to take questions. Thank you.